We have just seen how to solve the global minimum variance portfolio using the system of linear equations. There is also an alternative derivation for the same problem. And this alternative derivation is actually the analytical solution of the problem instead of using the Gaussian elimination to solve the system of equations that we obtained from the first order conditions. So you can call this alternative as the direct solution, if you like. And in this way, we still have our first order conditions as before. There is no difference here. But this time, for the first equation, we can write down what is the solution for our optimal portfolios that we are looking for. And this is the solution that is given in terms of this Lagrangian coefficient lambda. And next, we can multiply both sides by the 1 transpose. So this is a row vector. And we can use the second equation to solve for lambda, because we need to substitute our lambda value in this solution for the optimal weights. And if we do that, basically 1 equals to 1 transpose m. And basically this is equal to what we have here in terms of this lambda, right? So we are using this equation. We are multiplying both sides by this 1 transpose. So basically, since 1 transpose times n, or m transpose times 1, these are the same, because this is a scalar at the end, so you can take the transpose of this term, it doesn't matter as well. And this can be written in this form. And here, if we obtain lambda, lambda is given as, because this is equal to 1, as you can see, so lambda can be obtained as this expression here. And then you can go ahead and substitute back your lambda here. And that's going to give us this whole term here. And then by simplifying these terms and with these minus signs, we can get rid of them. So basically, the optimal portfolio weight can be obtained analytically using these direct substitution method. And next, we will talk about the Markowitz algorithm. And the difference from the previous setup here is basically now we have a target, we will have a target return, okay? So we will focus on this problem 2. So problem 1 and problem 2 are equivalent problems. In the first one, actually, you can maximize your expected return for a certain level of target risk. And in problem 2, which is the more traditional and conventional setup of the problem, is to consider the portfolio variance. We minimize this variance for a given target return level. And also, as usual, we have our total investment weights equal to 1 as a constraint. So in this case, we can set up our Lagrangian as before. And different from the global minimum variance portfolio problem, this time we have this additional constraint, which simply says this time we have a target expected return of mu of 0. And therefore, in this case, we will have 2 Lagrangian coefficients coming from 2 different constraints. And if we write down the first order conditions, now we will have these 2 partial derivatives with respect to lambda 1 and lambda 2. And you can see that our partial derivative with respect to each of these xi value is represented here. And then we also have the derivative with respect to x that brings us lambda 1 times mu. And from the second constraint, you can see the derivative with respect to x terms bring us lambda 2 times this vector of 1s. So basically, once we write these, then the next thing is to represent these first order conditions as a system of linear equations. Basically, this is a system of linear equations. And this can be represented. Notice that this is the vector of unknowns that we are trying to solve this system for. And this x contains basically if you have 3 assets, this x is going to be 3 by 1, and if you have n number of assets, this x is going to be n by 1 column vector. And similarly, you can see that the covariance matrix here will be proportional to the number of assets you have. So the rest of the problem is simply following the same setup, and basically this is your coefficient matrix A of x, and this is the unknowns that you are looking for, and this is your right hand side in this equation. And the direct inversion method gives you the solution. But if this coefficient matrix is a large one, and then if you want to do this calculation more efficiently, actually you can use the LU decomposition method that we have seen again in this chapter.